Okay, so today we will cover the topics which are related with the WRE, and I will try to cover the hydrology cycle, evapotranspiration, then infiltration, then flood routing, then reservoir capacity and groundwater hydrology. Okay, so we'll commence with our first topic, that is the hydrologic cycle. Now, hydrologic cycle, as name itself suggests, it's a conceptual model that describes the storage as well as the movement of the water between the biosphere, atmosphere, and the hydrosphere. Your water can occur in three states, that is the solid, liquid, as well as the gaseous state in nature, and all these phases are occurs in the large quantity. Depending upon the environmental condition and the place of occurrence, water can change its form very quickly. Now, hydrologic cycle can be visualized as a series of stories and set of activities that move water among these storages. Among these, ocean is the largest reservoir. It's holding about 97% of the earth water, and the remaining 3% of the fresh water and 78% is stored is in the form of ice in the Antarctica and the Greenland, and about 21% of the fresh water is on the surface of Earth in the form of groundwater. Now, hydrologic cycle considers the motion, the losses, the discharge of Earth water. It connects the atmosphere and two storage of Earth system, the ocean and the land sphere. When water leaves the atmosphere through precipitation, the ocean receives water from the atmosphere by means of precipitation. Okay, here in this figure we can observe, and from the land through the rivers and groundwater flow. Water goes out of the ocean only through the evaporation. The water leaves land through evapotranspiration, stream flows, groundwater flows, etc. Evaporation and precipitation processes take place in the vertical direction or vertical plane, while stream flow and groundwater flow occur mostly in the horizontal. Okay, so this is the schematic of the hydraulic cycle, hydrological cycle, which we will observe on the Earth system. Now see what will happen. A water will come on the land system in the form of precipitation. Okay, then that precipitation will be sustained by earth or the ground surface in the form of exfiltration or infiltration, and part of water will be going to get into the form of runoff. But runoff is nothing but the surface water or the running water. Then some part of the water from the runoff will add to the stream flow, and some part of the water will add to the groundwater table, and it will again lead to add to the aquifer system. Then part of the aquifer will go to the evapotranspiration, part of the subsurface water system will go to the evapotranspiration, and part of the land system water will go to the evapotranspiration. Evapotranspiration we will see in the next couple of slides. From again evapotranspiration, the water will convert it to the cloud, and then again it will come back to the earth surface in the form of rain. Then again it will form the precipitation, and it will come on the land system, and the process will continue. So the exchange of water among the ocean, land, and the atmosphere was termed as the turnover of the water exchange. This turnover affects the global pattern of your movement of ocean water and gases in the atmosphere. Now there are so many components of hydrologic cycle. These components are evaporation, evapotranspiration, condensation, precipitation, interception, infiltration, runoff, and storage. These are the terms which we will use at a time when the process is come into the picture. Okay, so it is divided into the three major systems. The ocean being the major reservoir and the source of water. Then second one, the functioning or the driving force is the atmosphere. It is the carrier and the delivery of the water. And the third component is the land surface. Okay, so the amount of water available at a particular place changes with time because changes in the supply and the delivery. Now the major component of hydrologic cycle is your precipitation. So precipitation is in the can occur in the form of rainfall, either snowfall or this one. Rainfall, either snowfall, hail, fog, drizzle, then interception, storage, evaporation, transpiration, percolation, and runoff, etc. Okay, so the first term is your evaporation. Now evaporation of water takes place from the ocean and the land surface mainly because of the solar energy, because of the sun. The moisture moves into the atmosphere in the form of water vapor, which precipitates on the land surface or ocean in the form of rain, snow, or hail. Then the part of this precipitation is intercepted by vegetation or your building. Here in this figure we can observe the precipitation has been received by the buildings or the land surfaces, and the amount will reach to a land surface and a part will infiltrate into the soil and remaining water will run off the land surface to join the streamline. This stream finally discharges into the ocean and some of the infiltrate water percolate deep to join groundwater and some come back to the ocean or appear on the surface as a spring. The next process or the next term which we will come to know in hydrology cycle is your transpiration. So transpiration is basically occur when the evaporation occurs from the leaves or from the green vegetable. Evaporation will occur from the solid surfaces or from the uh, land surfaces, but transpiration will occur from the green surfaces or you can say from the biological surfaces. Transpiration occurs when plant takes in water through the roots and release through the leaves or process that can clean water by removing contaminants and the pollutants. The process of evaporation from plant is termed as your transpiration. Okay, it's like plants are sweating or exhaling. When human exhale, we release water as well as vapors. Then there is next process that is your condensation. Transpiration, when plant absorbs soil water through their roots, and this water can originate from the deep into the soil. Okay, plants pump the water up from the soil to deliver nutrients to their leaves. The combination of evaporation and transpiration is termed as your evapotranspiration. The next definition is your precipitation. When the water in the cloud gets too heavy, the water fall back to the earth and this is called as your precipitation. The next one is your runoff. Runoff is the movement of water, usually from precipitation, across the Earth's surface towards streamlines, lakes, oceans, or low points on the Earth's surface. Okay, so runoff is nothing but the movement of water. It is the extra quantity of water which will remain on the earth's surface after the percolation, condensation, evapotranspiration and infiltration process. The characteristics that affect the rate of runoff include the rainfall duration and intensity as well as the ground slope. Then next very important term, that is your evapotranspiration. हाँ सर. ये आप भी वाला कर दो. ओके ठीक है. हाँ. मुझे एक चीज बताओ, तुम जब इसके मार्क एंटर कर रहे हो Okay, sorry for disturbance. Next is your evapotranspiration. Now, evapotranspiration can be defined as the sum of all form of evaporation plus the transpiration. So, B includes, it is simply combination of evaporation as well as transpiration. Evaporation is the loss of water from the soil surface and transpiration is your loss of water from the green bodies or from the plant surfaces. Okay. So when plant transpiration happens, the water is evaporating from the leaf surface. So we leave the breathing. Just because you don't see what doesn't mean it is not being put into the air. Though one way of visualizing transpiration is to put a plastic bag around some plant leaves as here in this picture we can see, we can observe around the plastic bag there will be water droplet. Hence we can observe that transpiration is a process which is actually happening over here. Okay, so this is what difference between a transpiration and evaporation has been shown here. Transpiration is a physiological process, whereas evaporation is a physical process. Okay, physiological just because of this is happening out of the biological bodies to the green bodies only, and evaporation is happening because of the solid bodies. It is transpiration, it is a loss of water from the free surface, and evaporation is a loss of water from the free surface of water. Then transpiration is a regulated process and evaporation is non-regulated. Transpiration is a regulated process just because of it is happening day and night or 24/7. But evaporation, for evaporation we need the running or driving force, that is the sun. More will be the temperature, more will be the transpiration, evaporation. If the temperature will drop down, the process of evaporation will lowers down. Then the transpiration is happen because of the guard cell, that these are the cells inside the biological component and there is no role of guard cell into the evaporation. It is comparatively slow process and evaporation is a faster process. Transpiration is influenced by the anatomy of the plant and there is no such influence of anatomy when we are talking about evaporation. So these are the factors which affect the environmental factor which affect the transpiration or the evapotranspiration, that is the temperature, relative humidity, wind and air movement, and type of plant. Okay, so that The rate will go up as the temperature goes up. Okay, then the humidity, as the relative humidity of air surrounding the plant rises, transpiration rate falls. Then wind and air movement, increased movement of air around the plant will result in higher transpiration rate. Okay, then type of plant, as the plant transpirate water at different rates. Some plants which grow in arid regions such as uh, succulent, the precious water by transpiring less water than other plants. Then there are two types of evapotranspiration, that is potential evapotranspiration and actual evapotranspiration. Now, what these two terms mean? Potential transpiration or potential evapotranspiration is a measure of the ability of the atmosphere to remove the water from the surface through the process of evaporation and transpiration, assuming no control on water supply. And actual evapotranspiration is the quantity of water that is actually removed from the surface due to process of evaporation and transpiration. Means potential evapotranspiration will measure, or it is a quantity of water from the surface through process of evaporation and transpiration. Here there is no control of water supply, means whatever inflow is there, there is no relation of inflow to the outflow. But when you are talking about actual evaporation, it means you have to make difference between inflow and outflow, that is the amount of inflow quantity minus amount of evaporation will give you the actual evapotranspiration quantity. Okay, so to measure the evapotranspiration we have a device that is termed as or named as the decimeter. Okay, so decimeter is a device for the direct estimation of evapotranspiration, and typically it comprises a vegetated block of soil around 0.5 to 1 liter, due to which the amount of water added and is known, and from which the amount lost as a runoff or percolation may be measured. Recording the changing weight of the soil vegetation system reveals the amount of water retained by the system, and thus by the difference the amount lost as evapotranspiration. So by recording the amount of precipitation that an area receives and the amount lost through the soil, the amount of water lost by evaporation can be calculated. Okay, so AP will be calculated as P plus I minus B plus S, where EP is evapotranspiration, P is the precipitation, I is irrigation water, D is excess amount of water that will be drained out of the bottom, and S is increase or decrease in the storage of soil. Okay, next process is your infiltration. So the process of entering the rainwater into the soil strata is termed as your infiltration, or the amount of water that will percolate or that will enter into the soil strata or ground strata is termed as your infiltration. So the process of infiltration, it first meets the soil's moisture deficiency. If there is deficiency or if the soil is dry, so first the infiltration water will fulfill the moisture in deficiency into the soil, and then the extra amount of water will move vertically downwards to reach the groundwater table, and this vertical downward movement of water is termed as your percolation. Okay, so percolation and infiltration, these two are two different quantities or two different characteristics of groundwater. Infiltration is the total amount of water that will get infiltrated into the soil. But percolation is the amount of water that will add to the groundwater table after removal or after fulfilling the soil moisture deficiency if available into that soil strata or into that hearth rhythm. So the infiltration capacity of soil is defined as the maximum rate at which it is capable of absorbing water and is denoted by F. If your infiltration capacity is greater than F, that is the soil factor capacity, then your FA will be taken as F, that is your infiltration capacity coefficient will be taken as the F, that is the infiltration capacity. And if your I, that is the rate of rainfall, is lesser than infiltration capacity, then your actual infiltration capacity will be taken as the rate of rainfall. When your soil is dry, your F is more, F is nothing but your infiltration capacity is more, and when it is moist, definitely infiltration rate or infiltration capacity will be less. Okay, maximum rate of water absorbed by soil is nothing but your infiltration capacity, and maximum capacity of water absorbed by soil is the field capacity. More will be the dry soil, more will be the infiltration capacity, and more will be the field capacity. But if the soil condition is in moist, then infiltration capacity is lesser and field capacity is higher. Hello? Okay, so it will be termed as a field capacity. So there are few factors which affect the infiltration capacity. These are the precipitation, then base flow, then soil characteristics, then soil saturation, then land cover, then slope of land and evaporation. So these factors will affect the infiltration rate or infiltration capacity. Okay. And next term is your hydraulic conductivity. Hydraulic conductivity is the ability of a fluid to flow through a porous medium. That is, it is the phenomena related with the infiltration, and it will define the ability of water or the fluid which will flow through the porous medium. It is determined by the size and shape of the pore space into the media and viscosity of the fluid. Okay, so we have gone through it, that factor affecting the infiltration capacity. First factor which will affect the infiltration capacity is the slope of land. More will be the slope, more will be the infiltration rate and degree of saturation. The more saturated the loose earth materials are, the less acceptable to the infiltration. Then porosity. Porosity is the percentage of open pores or the open space in the earth surface. Greater the porosity, greater will be the amount of infiltration. Then the next topic is hydrographs. Now, what are the hydrographs? A hydrograph is defined as, for instance, a hydrograph is a graph showing stage, discharge, velocity, or other property of water flow with respect to time. When the stage is plotted against time, the graph is a stage in hydrograph, which is the form of string gauge record, and the discharge is shown against the time. The graph is a discharge hydrograph. Or in the simplest form, I can say it is the simplest form. A hydrograph is a graphical representation of a runoff rate against the time. Okay, so this is nothing but a graphical representation of runoff rate against the time. On the x-axis we plot the time, and on the y-axis we plot the precipitation as shown in this figure. It shows the time distribution of runoff at a point of measurement or computation. The figure reflects the complex characteristics of your watershed by a single curve. Okay, so this is the time versus discharge graph, and it is termed as your hydrograph or natural hydrograph. Now, there are several types of hydrograph. One is your natural hydrograph, then unit hydrograph, then dimensional hydrograph, synthetic hydrograph, dam hydrograph, etc. Out of which unit hydrograph has the more importance. The first one is your natural hydrograph. Natural hydrograph are one recorded at a stream gauging site and as a fingerprint of upstream drainage area. Then there is unit hydrograph, which is of our use. Unit hydrograph is the amount of runoff resulting from one unit, that is 1 centimeter or 1 mm, 1 feet of excess rainfall. Or in other words, I can say a unit hydrograph is a natural or synthetic hydrograph representing 1 centimeter of runoff uniformly for the watershed during a specified time. Okay, so when we are talking for the unit hydrograph, it will represent a graph for the unit quantity of discharge for that particular watershed or for that particular catchment. Okay. Now there are few terms which are related with the runoff discharge. Now first one is the peak discharge. As the peak or the apex of this curve is nothing but the peak discharge. Then there is a falling limb. The right hand side limb is nothing but your falling limb. Then there is rising limb. The left side of the curve is the rising limb. Then from the first approach segment to the center of the peak discharge is termed as your lag time. So these are the terminologies we should know before plotting the hydrogram. There are few assumptions which we have to made before going for the plot of the unit hydrogram. So assumptions are the effective rainfall is uniformly distributed within its duration. That is, whatever amount of discharge we are plotting, it is uniformly distributed during the catchment period. For an example, for 7 hours we have to plot, for 10 hours we have to plot. So the rainfall distribution is uniform. Then the effective rainfall is uniformly distributed over the whole drainage basin. Then the base duration or the direct hydrograph due to an effective rainfall of unit duration is constant. The ordinate of direct runoff hydrographs are directly proportional to total amount of direct runoff of each hydrograph. For a given basin, the runoff hydrograph to a given period of rainfall reflects to a combined physical characteristic of basic time invariant. Basin time invariant. So we'll go with one example. See here in this problem, a physical 6-hour storm 4 centimeter excess rainfall is occurring and the flow recorded in the catchment as shown in below derived and unit hydrograph of 6-hour storm. Assume base flow in 100 cubic meters per second. Okay, so you have to plot unit hydrograph of the direct runoff hydrograph. First of all, what we will do? We are given with the time and observed hydrograph units. We will plot this. Okay, and we are given with the 4 centimeter excess rainfall data. So direct runoff hydrographs are given to you. So we will plot all the ordinates of direct runoff hydrograph. Okay, that is DRS, and then we will write down the base flow. Now here the base flow is 100. Okay, the first one you can see 100 meter per second is your base flow. Okay, so we will minus the base flow from the all ordinates. Base flow is nothing but the common amount of flow which we will get and after you can say it is the infiltrated water, and the remaining amount of flow is your runoff. So we will, for getting the direct runoff hydrograph, we will reduce 100 from the column number 2. Okay, so 100 minus 100 is 0, 100 minus 100 is 0, 200 minus 100 is 200. So you will get the direct runoff hydrograph. Then for getting the ordinates of unit hydrograph, you are given with the 4 centimeter of excess rainfall. You have to plot for 1 centimeter. So divide all the ordinates by 4. So you will get the ordinates for unit hydrograph, that is 200 divided by 4, that is 60, 600 divided by 4, that is 150. And then you will again plot time versus column number 4, that is ordinates for the hydrograph. So you will get a graph which will show your graph for the 1 centimeter of excess rainfall for that given catchment. Okay. Now your next topic is flood routing. Flood routing is, what is flood routing basically? Flood is when, what is happening when flood will come. A river is normally at the level at which the river overflows its banks and surrounding areas, and it will damage by the flood in terms of loss of life, property, and economic loss due to the disruption of economic activity. So, what we have to do, we have to reduce that flood peak, or we have to lag that flood peak. Is it? So, at any given location in a stream, the flood peaks vary from year to year and their magnitude. To estimate the magnitude of flood peak, the following methods are used: rational, either empirical, frequency, or unit hydrograph techniques. So, flood hydrograph is basically, or flood routing is a method basically that is applied to describe the process in the water course, and it is used to predict the temporal flood waves at one or more points along all water course. It means flood routing is basically a method in which we represent, or the stage and discharge hydrograph represent the passage of wave of stream depth and discharge respectively. In this wave moves down, the shape of the wave gets modified due to channel storage resistance and lateral additional or withdrawable flows. So basically in flood routing, what we do, we have to reduce the peak of the hydrograph. Second one, that is what does it mean? It is termed as the attenuation of the peak flow. Okay, the reduction in the peak flow of the hydrograph is nothing but the attenuation. So we have to first do the attenuation of the peak flow, and we have to lag the attenuated peak. That is, whatever time it will come, when flood will come, or when the river basin will get over flooded, and we have to lag that time period, and we have to reduce the peak that hydrograph. So this process is nothing but your flood routing process. So here see in this figure, figure 1 is a basic figure. So if we will try to attenuate the peak flow, and we will try to lag the time period of attenuated peak flow, then this is your flood routing. Then flood routing can be classified as hydrologic computational method which employ both the equation of continuity, and there is hydrological method used for the rainfall runoff model. To do the flood routing, there are basic equations which are taken from the hydrological routing process only. Okay, these equations are like discharge is equals to discharge of surface plus inflow plus basis plus channel. So we have to take account of all the discharges, out of which the total quantity of water will come into your basin. Okay, what will happen in upstream side when there is the velocity, when there is less velocity and the flow is quite stable, the flood routing should not be done or it may be avoided, but when water will come to the downstream side, its velocity will increase. What will happen? There may be chances of sudden attenuated, or there may be chances of sudden increase into the velocity of water, and because of which what will happen? There may be chances of the damage to the reservoirs or the banks or garages. So just to avoid it, we have to look on the hydrographs of the inflow of the water, and that attenuated inflow water is termed as a flood routing method. So routing methods are kinetic wave method is there, then dynamic method is there, then Muskingum method is there. By using these methods, we can drop down the peak of the given hydrograph. Okay, these are the methods of flood routing. So your next topic is flood reservoir capacity. Now, as the name itself is suggesting, what is capacity? Capacity is nothing but the gross volume of water which can be stored into the reservoir. Okay, so the reservoir capacity is the means the gross volume of water which can be stored into that reservoir which we have built. This is the schematic diagram showing the storage zone or the storage capacity of the given reservoir. Okay, so there are certain levels into the reservoir which we come to know or which we should know before going for the design or before going for the analysis of any reservoir. Now, there can be dead storage capacity, means the portion of the reservoir capacity which is not in use or which is not in the operational use. Here see, you can see so many different nomenclatures like foundation level, dead storage, and stroke, spillway crest level, then there is top of flood control, then subcharge storage, then there is freeboard, top of dam is there, and the mean water level is there, then top water level is there. Then there is a bed level. There is still storage capacity and inactive storage capacity. So each and every term has its own meaning or its own definition. Okay. So the reservoir capacity is computed on the basis of land area and varies by the type of the land use, either it is residential, commercial or industrial. So first one is your dead storage capacity. Okay, so the capacity which is not in use or which is not in the operational use is termed as your dead storage or dead storage capacity. Then there is live storage capacity. Live storage capacity means the reservoir capacity excluding the dead storage capacity. Live storage capacity means the corresponding volume of water flood storage capacity means that portion of reservoir capacity which is reserved for the temporary storage of the flood water in order to regulate the downstream flow. Then there is flood storage. Flood storage is the corresponding volume of water. There is surcharge storage capacity, means the reservoir capacity between the crest of an uncontrolled spillway. Then there is a conservation storage capacity, which is used with reservoir capacity excluding the flood storage capacity. Okay. And at the end, there is a general capacity. General capacity means the conservation storage capacity, excluding the power storage capacity. At the end, there is a dead storage level. Okay, at the end, bottom you can see dead storage level DSL. DSL is exclude any DSL level is the level of water in a reservoir corresponding to dead storage capacity, below which the reservoir does not operate. Okay, so below the DSL level, there is of no use. This is not of our use. The last one is the full reservoir capacity, a full reservoir level, FRL. So FRL level is the level of water in a reservoir corresponding to conservation storage capacity. Okay, here I have mentioned two definitions. First one is a full reservoir level. It is the level corresponding to the storage which includes both inactive and active storage and also the flood storage if provided for. In fact, this is the highest reservoir level that can be maintained without spillway discharge or without passing water downstream to the spill source. The minimum drawdown level, that is MVDL, it is the level below which the reservoir will not be drawn down so as to maintain a minimum head required in power supply. And there is a storage level, that is DSL. Below this level there are no outlets to drain the water. Then maximum water level, MWL, this is the water level that is ever likely to be attained during the passage of design flood. There is a live storage. This is the storage available for the intended purpose between the fully supply level and the inward level of the lowest discharge outlet. The full supply level is normally that level above which overspill to waste would take place, and the minimum operating level must be sufficiently above the lowest discharge outlet to avoid the vortex formation and air entrapment. This may also be termed as the volume of water actually available at any time between the dead storage level and the lower of actual water level and full storage capacity or full reservoir capacity. Then there is dead storage. It is the total storage below the inward level of the lowest discharge, and outlet surcharge or the flood storage is the storage reserve between full reservoir level and the maximum water level. Okay, so these are all definitions related with the reservoir capacity. After reservoir capacity, we have very important topic, that is your groundwater hydrology. So before going for groundwater hydrology, you should know that what is groundwater. So groundwater is a water that exists into the pore space, that is into the voids of the soil or strata or the earth strata, and fractures into the rocks and sediments beneath the unsaturated zone of water, unsaturated zone of soil, which can flow freely into the well. Okay. So groundwater hydrology, as we have already seen, there are few terms, that is rain. Rain is nothing but which will fall on the earth surface and it will enter into the land surface. Some of some of water will flow over the land surface, that is termed as your runoff, and some will enter as an interflow, as a percolation or interception just below the surface of land. Okay, so there are few formations. So there are type of geological formations which we should know, and these are termed as your aquifers. So what are aquifers? In order to understand the groundwater potential in any area and to evaluate the impact of your pump groundwater agent, we should know the aquifer capacity or about the geological formation. So aquifer is defined as a groundwater reservoir composed of geological units that are saturated with water and sufficiently permeable to yield water in usable quantity to wells and springs. So there are basically two types of aquifers. These are unconfined aquifers and confined aquifers. So aquifers are nothing but the bodies which will allow the water to flow out of its structure and which will allow water to drain out of its structure. Okay, so these are the geometrical combinations or the earth surfaces which will allow water to flow out of its structure, and the water can be drained out or can be abstracted out of the aquifer structure. Here see, as the water body or a solid mass water body has been shown into this picture. Here see, confined aquifer is aquifer which is sandwiched between two soil stratas.